First, we go to Fluent Flow Fluent, add to the system, and then go to New Design Model Geometry. With that up, we will go to select the XY plane, hit Z. I'm going to create 4 lines. Horizontal, 1, 2, only 3 horizontal lines. Then we're going to go to Dimension, Horizontal, first, or General. Mention this, it will be 1.1176 meters. Next one will be this. It will be 1.2192 meters. Next one will be this. And it will be 0.889 meters. And we're going to draw 4 vertical lines. Dimension them. This one will be 1.6256 meters. This one will be, this one will be 0.6096 meters. This will also be 0.6096 meters, and this one will be 0.889 meters, and this length is actually going to be 1.5748 meters. And we'll go to constraints, midpoint, constrain the midpoint for this one to here, 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 and then here to here. Then what we're going to do is create new lines connecting all of these outer parts. And then with that complete, we will delete all of these internal components. Then we will go to File. Actually, before we do that, we're going to go to the workbench to update it. And then from here, we're going to directly duplicate it. This will be for part B. We're going to go back. And then we'll go to Concept, Surface from Sketch, Base Objects, Sketch 1, Apply, and Generate. Then with that, we'll go back to Workbench, update again, and then we will start our mesh. With mesh loaded, we center it, go to mesh, to insert, and then what we will do is create a body sizing, which is sizing, geometry, apply, type. Type will not be, it will be element size with a element size of 0.005 meters. And we will generate. Actually, we will stop this mesh. And first, before we do that, we will create a automatic mesh. Geometry here. Then we're going to select the triangles method and generate. Create a preliminary mesh. And then we will add our body sizing. With that done, we can look at our mesh, see that it looks nice and dense like that. We go back to the workbench, we update, we go to setup, and with setup we select 2 solver process, double precision, start. With it loaded, we'll go to models, set energy on, change it from viscous omega to that, and what we will do is we will set the enhanced wall treatment with pressure gradient effects and thermal effects. Okay. Materials, fluid, air. Actually, before we do this, we will go back into the mesh. Yeah, we will close this. Go back into the mesh. And from there, we will create our name sections. We will surface body. Our edge selector. We will select these edges. Create name selection. That will just be walls. To select this, create name selection. That will be inlet. Select this part, create name selection. That will be outlet. Okay. And we'll go back here. We'll update it. And then we'll launch the setup. Load new mesh, everything. Once again, double precision 2 solver processes. Again, with that loaded, we will double check that it is, again, viscous standard K epsilon with enhanced wall treatment, pressure gradient effects, thermal effects, energy on, materials, fluid, air, and that is, we'll take the density as ideal gas. Actually, yep, ideal gas, change create. And we'll go to boundary conditions, inlet will be inlet. That would be wall for walls, outlet, outlet. Double check that it looks good. And for the input velocity magnitude, we will do 5.625 because that, when calculated, gives us the desired velocity specified in the project. Outlet, pressure outlet. Double check that. Prevent reverse flow. Yeah, prevent reverse flow. Walls. We will apply no slip. Yep, stationary, apply. Double check the reference values. That looks good. Methods, scheme, all looking good. Then in initialization, we'll hybrid initialize. Then we will run the calculation with, say, 150 iterations. Now with the calculations complete, we will go down to graphics, contours, select all of that, and we will do contour for pressure. Same display. There we go. Contour for the total pressure. There. Contour for the dynamic pressure. And then we'll get the contour for the velocity. All right, all looking good. And then we will go and create the streamline. So path lines. Okay, that's encountering problems, so we'll just not do that. Or, well, okay. Well, hmm. Alright, I don't know what's going on, so I'm just gonna save, then restart this thing. Okay, so with that hiccup solved, we're going to instead do the streamline in post. What we are going to do now is going to go to plots, XY plot, and then we're going to add a new surface. This is from point. Actually, this will be a new surface, new line, x0, going out to x equals 3.8846. This will be for the center line. New one is going to be from, both are going to be at x equals 1.9423 and x equals 1.9423, but this time it will run from y equals 0 to y equals 0.6096. This would be the vertical. What we're going to do is first we're going to plot it along the center line. And so here we are going to plot the, we can also write the file if you want, but there's the static pressure, which, let's create a new center line. Let's try negative 1.9423 to 1.9423. Let's plot that again. Okay, so in that case, static pressure should not look like that. Let me try a new line. From x equals, again, x equals 0 to try x equals, hold on. Okay, let's try that again. Again, center line, pressure, static pressure. There we go. And now we gotta find along the center line the total pressure. Don't worry, it looks squiggly. That's fine. It's actually a very small range, just zoomed in a really big amount. Then we will go to check the dynamic pressure. That looks good. And we will also check the velocity. Yeah, it looks good. And then along the vertical, we will check the velocity as well. That, actually, let's reorient it. Looks about right, though we will update the vertical to go from like also from 1.9423 and 1.9423 and from negative 0.3048 to negative 0.304, sorry, to positive 0.3048. Call that vert2, create We'll measure along vert2 velocity. Yep, that looks good. Then the dynamic pressure. Yep, that looks good. And the total pressure. Yep, that also looks good. Now we will go back to the workbench. We will save it. Then we'll go into results. Now in results, what we will do is create a new streamline, call it streamline 1. Start from the inlet, number of points, let's call it 100. Variable velocity, apply. There it is. Looks a little crowded. Let's bump it down to 50. Yep. And those streamlines all look pretty good. So then we'll go back, double check the save. With it saved, we'll go back into the geometry, and this will be for part B. Okay, loading up. Go back to the sketch. There we go. Let's just take a minute to get everything oriented. Go. Orient it. Sketch selected. We will go to sketching, and we will add a circle. And we will dimension that circle to have a diameter of 0.0696 0.06096 meters. And what we will do is we will constrain it so that way it is parallel. Actually, what we'll do is sketch, draw, line, do this, create an X in the middle. That point is where we're going to put the midline. So constraint, midpoint, that, that, right there in the middle. Then we will just go in and sketching, line again. Let's try just putting the midpoint here. Yep. Seems good. Delete that. And that's our cylinder in the middle. And we will go to concept, surface from sketch. We will take this sketch, apply, generate. And with that done, we can move on to the new mesh. We'll check it's updated. Then we will create the mesh. Now here, we can go to the mesh. First thing we're going to do is going to insert a sizing. We'll make it edge sizing along this. Type will be a number of divisions. Set number of divisions to 200. Capture curvature is no. The behavior is hard. No bias, and we will generate this first. Okay, there's the start. Then we're going to insert and inflation again along this circle here. Apply. Actually, geometry will be this here. Boundary will be this here. And for the inflation, we will have the maximum layers be 50. Inflation option will be first layer thickness, first layer height will be 0.01, -2, generate. Look like that. And then we're going to, in the overall mesh, what we will do is change the element size from the default standard to 0.004, and we will generate. There we go. With that all nicely done, we will go back to the workbench. We will update. And with that, we can move on to the setup. Again, with the setup, dull precision, 2 solver processes, start. With that loaded, again, we will go to models. Energy is on. Viscous will be set to K epsilon with enhanced wall treatment, pressure gradient effects, and thermal effects enabled. Materials will be fluid, air, will be again ideal gas, change create. Again, I realize we did not. Alright, so we're going to close. We're going to close the setup here. And we're going to go back to the mesh in order to create our named sections. Again, 1, 2, 3, 4, 5, 6 will be the walls. This will be the inlet. This will be outlet. And in here we will have our cylinder. Here. Update. Save. And again, back to the setup. I'm gonna update it all. Start. Okay, loading. Setup back up again. Just double check everything looks good. Materials, fluid, air, boundary conditions, inlet, inlet, wall, cylinder walls. Again, both of these are stationary with no slip conditions. Outlet, outlet. Okay, reference values. Actually, I'm going to go back to boundary conditions. Inlet. Set the velocity to 5.625. Again, apply. Reference values. Compute from inlet. Again, all looks good. Initialization. Initialize. One calculation. Number of iterations 150, and calculate. All right, with that complete, we can move to our contours, velocity and pressure for this. So select all of these surfaces, static pressure, we go. That looks good. And then we're going to velocity, velocity magnitude. That looks good. And we go to XY plots over here. And this you need to write to a file um, because Fluent uses the incorrect velocity, uses the velocity of the inlet and not the velocity in the test section. But in general, pressure coefficient looks something like that. And then from here, we need to go to force report, cylinder, and we use this to get the total drag force. And then from there, you manually calculate the drag coefficient because, again, Fluent uses the velocity of the inlet and not the velocity of the actual test section. And that concludes parts A and B. My other group partner will conduct part C, which I will cut in starting now.
Okay, so this is part 3 for the fluid mechanics final project with Dr. Osprey in the summer of 2025. It is the small, thin, flat plate in a wind tunnel. So we will start from the workbench. We'll drag it over. We'll start from the workbench. Don't mind these. We're gonna use this one. I already have them open just for ease of access, so we're gonna go the geometry first. This is the geometry of the wind tunnel. It follows the assigned parameters of the wind tunnel, and then in the middle of it was drawn by using these 4 vertical lines that were connected to the 3 sections. So at one point there was a line that connected this section to this section, this section to this section, and this section to this section. All of the lines were added together, and the surface was made from the sketch to make the wind tunnel. Following that, there was a thin flat plate added to the middle of the sketch. As you can see, it is right here. It has a height of 0.0005. And this little length right here is just to center it on the middle of the wind tunnel. And then this is the half-meter length that the entirety of the wind tunnel had to be. So we made the surface from the sketch very small. This is the thin flat plate in the middle, and it is centered in the middle of the test section of the wind tunnel. So once we did the geometry, we moved on to meshing. This is what the geometry looks like when it first comes into meshing. We named our sections the velocity inlet the left side, the pressure outlet the right side, the walls of the wind tunnel, and then the flat plate itself with all 4 walls selected in the wind tunnel itself. I hate when it does this. All right, and then for meshing, maybe? Never know. We should be able to see the meshing in just a moment. Oh, that's not what I wanted to do. Well, that sucks. Something definitely just happened with the meshing, but that's okay. Anyway, here is our the edge sizing that was around the, well, this is supposed to be around, this is on, well, the edge sizing on the top and bottom of the flat plate, and then the edge sizing on left and right of the edge plate. Notice that the left and right is significantly smaller than the top and the bottom. Don't know what edge sizing we got rid of, but hopefully it's okay. So that is what the meshing looks like, and if you notice, it is very fine around the edges, especially in the front and in the back of the plate. Very small, and if you zoom out, you can't even really tell that there's meshing. It just looks like a block in the middle. And then, so now we can run over here and do show our contours. Just for reference, these are our reference values. We are using an ideal gas. We're we're using an ideal gas. So it's labeled as ideal gas right there, which that changes our density of air, and then our boundary conditions, we have the velocity coming in at 5.625 meters per second. And then nothing is going on here. The walls are stationary with a no slip condition to just help everything out. So once again, these are our reference values taken from the velocity and the density, a little bit different. And then the methods, this is what the method looks like. And we did change this as well. I forgot to mention it to, instead of the ones up here, we did this with a standard thing and then enhanced wall treatment so we could get the best possible results. And then we initialized 25 times and then we ran the calculation. This is what we ran 200 calculations. Okay. This is, well, that's basically what the scaled residuals look like. Um, and then we ran the calculations 200 times and it came up with this. And then so the first thing that we will show is the pressure contour. And if you notice, you can't even see the flat plate here, but if you zoom in a lot, you can see the pressure contours on the velocity inlet edge of the flat plate. And you can see our clovers coming back. And then if you zoom out, there's not really anything going on the right-hand side or the pressure outlet facing side of the pressure contour. It's just kind of, there's a little bit higher pressure over here, but not too much. Or lower pressure, I guess. And so that's what the velocity contour looks like. And then the pressure, or I'm sorry, the pressure contour. The velocity contour looks like this. And the most important thing here is this wake region at the end on the pressure outlet side of the plate. And then this is what the inlet side of the plate looks like. There's a little bit of like turbulence going on, but nothing crazy. So that's what that looks like. And then our skin friction graph looks just like this. Not really much going on here. You have the skin friction coefficient going on over here and the position on the x-axis. In the report, both of these are put into an Excel and been non-dimensionalized. And then for our wall shear, it looks virtually the same position on the x again of the wall shear in pascals on the right. And again, this has also been put into Excel. If you notice, they are pretty much the exact same graph. And then we can show the drive forces down here. So that's what that looks like. Yeah. Okay, so now that we have done our pressure contour, our velocity contour, and then also our wall shear and our skin friction. We can move on to the drag coefficient. So for that, we're going to go down here to forces, and then we'll take it from the top of the plate. If we take it from the entire plate, it will work out as well. So we'll select the top plate, and then we will get that the total drag force is 0.3538. And if we non-dimensionalize that, we will get a drag coefficient of about, oops, that's the wrong one, of about 0.00535.